Good morning. My name is Jason Wilson, and I am a network engineer at Dropbox. A little bit about Dropbox. We have over 500 million registered users, more than 200,000 enterprise business customers, and roughly 1.2 billion files are saved on our platform every day. Today I'm going to talk about how we built a multi-terabit network in about a year to support the migration, storage, and serving 500 petabytes of user data. I'll share some of the challenges that we faced and associated solutions, as well as some insights and lessons learned from the experience. Dropbox was built utilizing a hybrid cloud architecture. We stored metadata about our users and their files in our data centers, while the actual data or file content was stored in AWS S3. Well, this hybrid approach allowed us to scale very quickly. As we grew larger, we decided that we needed to invest in our own in-house storage system. There were a couple motivations behind this. Having control of the entire stack end-to-end allowed us to improve performance for our exact use cases. Further, it allowed us to leverage these specific use cases to customize software and hardware, which resulted in cost optimizations. And so, Magic Pocket was born. Many years ago, in marketing material, we called Dropbox a Magic Pocket because it kept all of your files in one convenient, safe place. So we named the storage system, the team that built and supports it, as well as the overall project, Magic Pocket. More specifically, Magic Pocket is a distributed, multi-exabyte, immutable block storage system. For the network engineering team, Magic Pocket was a tightly coupled set of challenges that we had to execute upon in parallel and very fast. We had to build an edge to provide our users with reliable, optimized access to their data. We had to build a backbone to pull that data out of S3 and replicate it across regions. And finally, we had to build data centers and light them up with servers, so we had a place to land all that data. I'm going to give you a high-level timeline here to provide some context. August of 2014 was our dark launch. We began storing some user data in Dropbox data centers, mirroring it between regionally diverse locations, while still keeping copies of this data in S3. February of 2015 was our actual launch. After extensive validations, we for the first time stored and served some user data exclusively from our own infrastructure. In April of 2015, we had built up our confidence in Magic Pocket, and we were ready to go all in. We had a very tight timeline in which to complete the bulk of the migration before we'd have to renew our very large storage commit with AWS. This tight timeline left very little room to open the parachute, as it were, so we called this part of the project Base Jump. Our goal was to serve at least 90% of user data from Dropbox infrastructure about October 30th, 2015, and we were successful, actually hitting our goal early on October 7th. To build our network, we needed the United States of America, obviously. We had three high-level areas of focus: edge, backbone, and data center. I'm going to start at the edge and work my way in. The edge provides three key things for us: transit, how we connect to the world; peering, how we augment and improve that connectivity; and performance optimization, how we get closer to our end users and improve their experience. Our best-in-class performance is a key differentiator for us. And it provides us with a real competitive advantage. Further, more than 50% of our users are outside the US. This means that the edge is an absolutely critical part of our infrastructure. To have an edge, you need POPs, or points of presence. Our POPs are co-locations in well-known, carrier-neutral internet exchanges. Utilizing POPs greatly simplified the process of augmenting our transit and transport capacity while our network quickly scaled. It also laid a foundation for peering and performance optimization. Our POPs serve multiple purposes for us. They provide internet connectivity via transit and peering. They also serve as transport vertices in our backbone. Our POP footprints follow two high-level patterns. The first is POPs in data center metros. Because they provide interfacility and internet connectivity for our data centers, we deploy them in pairs for redundancy. And each of these POPs has a minimum of 2 peering routers in addition to multiple backbone routers. The second is POPs outside of data center metros. These locations are significant from a transport perspective, a peering perspective, a performance perspective, or some combination of the three. Transit. As Magic Pocket ingested more data, more users were pointed away from S3 and toward our infrastructure, and our applications handling of locality matured. There was a significant amount of work required to distribute traffic across providers, connections, regions, and metros. By work, I'm referring to various forms of traffic engineering. We had a few issues that increased this amount of work. While we had the same transit providers in each of our data center metros, the capacity to them was very uneven, mostly because we were moving so fast. This meant that we couldn't fail traffic from one metro to another, and more importantly, when the application suffered a failure and causing traffic to shift to another metro, it often resulted in a service degradation. We also have very uneven ingress traffic across multiple connections from the same provider. Most large carriers can't support BGP multipath across routers due to the utilization of route reflectors. And finally, we didn't have global ACDR, or aggregate committed data rates, with our providers, with all of our providers. This meant that when traffic shifted unexpectedly, we would often incur additional cost for idle capacity. We've come a long way in resolving these issues. We now have equal capacity across all providers in our data center metros. We have worked with our providers to better distribute ingress traffic across multiple connections to them, and we now have a global ACDR agreement with all of our transit providers. Peering. A common misconception is the motivation for peering is largely financial. I'm not going to go into a cost analysis of peering versus transit, but I will tell you this. Peering for us really wasn't about reducing cost. It was about performance. While our goal of performance optimization helped drive the decision to build POPs and co-locate, we would have made the same decision motivated only by peering. Peering provides several tangible benefits. Provides control and visibility. It's much easier to troubleshoot connectivity or other issues when you have a direct connection and an established communication channel with remote ASN. Peering also allows you to pick up traffic geographically closer to your customer and backhaul it yourself, which means that you get to decide which traffic is dropped in the face of constraints, as opposed to a provider making that decision for you. Finally, peering can also help reduce your exposure to things like carriers playing chicken on saturated interconnects. To move 500 petabytes of data out of AWS, we needed an interconnect with Amazon. While their Direct Connect product was available, our requirements were ahead of the feature set at the time, most notably LACP, but also other capacity-related limitations. So, as a large AWS customer and partner, we worked with them on an interconnect solution, which allowed us to complete the data transfer in a reasonable time frame. In addition to this interconnect, we also sought out a specific transit provider with good regional connectivity and available capacity to AWS. This was an insurance policy / safety valve of sorts in the event that we encountered issues with the interconnect, technical, capacity, or otherwise. We made some great progress with our peering. In March of 2015, we had about 1 gig of peering traffic. Today, that number is in the hundreds of gigs. Our team's done some really great work in this area. We're currently working on making our peering policy a bit more selective and also working to improve how we differentiate and choose between transit and peering prefixes. Performance optimization. I mentioned earlier that we knew we wanted to be close to our customers and that we intended to land a set of servers in each of our POPs. These servers terminate TCP and SSL for our clients and optimize these connections back to the origins in our data centers. There were several things we had to do to prepare for this. We needed transit connectivity in all of our POPs, even the remote ones in metros without data centers, because a POP needed complete reachability if it was going to terminate client traffic. We also had to augment our routing policy. We previously shared peering prefixes between POPs, largely for simplicity, but also because it hadn't mattered up to that point. We also shared transit with a regional scope, which meant that a POP could learn transit prefixes from another POP. Both of these things had the potential to cause traffic to egress our network non-locally, or more specifically, to egress from another POP. This would have broken the assumptions that we and our traffic team had made about traffic flows. So we had to be more granular with regards to scope and a routing policy. In addition to locality and route type, we also had to consider router or facility type when determining which prefixes to send to a given IBGP neighbor. The next area of focus is backbone. We obviously had to build a backbone to connect all of our sites, and we had 2 transport use cases to solve for. The first was long-haul circuits to connect metros, and the second was intra-metro circuits where we located our data centers. For long-haul, we didn't have the resources to build an optical team, purchase IRU and long-haul dark fiber, and light it ourselves. Our traffic volume was too large for carrier-provided M or VPLS solutions. And even if it wasn't, we wouldn't have gone that route. We investigated the possibility of obtaining spectrum from carriers, but that didn't work out. Because we had chosen all-purpose carrier-neutral exchanges for our POPs, obtaining spectrum would have required us to land at least 2 racks of CPE gear in each of our POP cages. Building out to carrier-specific locations would have allowed us to obtain this spectrum without that gear. However, the cost associated with that build-out would have absorbed any savings provided by the spectrum. So we decided to go with lit managed waves. We didn't have 100 gig ports available on our routers yet, And 40 gig wasn't really a thing. 40 gig long haul wasn't offered in all markets, and regardless, we saw a significant cost benefit of 40 gig over a set of 10 gig waves. So we went with 10 gig waves and lots of them. We decided to initially utilize 2 national carriers to source these waves, and our goal was to have 2 diverse paths between each pair of metros with no SPOFs or single points of failure. This proved more difficult than we thought. We had at least one case of a provider giving us incorrect path information, which we used to make further purchasing decisions. This resulted in a SPOF across providers, which was discovered when a fiber cut impacted them both along a given point in our backbone. Probably the biggest challenge we faced with long haul was the volume of 10 gig waves on our backbone. Carrier maintenances, punctuated by the occasional fiber cut, resulted in our pager being really, really noisy. It was pretty common to be woken up many times in an on-call rotation, often with unactionable pages. For metro connectivity, it did make sense to obtain dark fiber pairs and light them ourselves using DWDM systems that we managed. This was more attractive than lit waves in the metro because it was more cost-effective and allowed us to add capacity faster. While the metro scope reduced some of the barriers to entry of managing optical, we still had a small team with limited relevant experience. We were able to overcome this by initially utilizing professional services provided by our optical equipment vendors for installation and certification of line-side connectivity between sites, while we built expertise in this area. As we built out our backbone and our traffic levels increased, we ran into several issues load balancing traffic under normal conditions and failure modes. Like any respectable network operator, we knew we had to use route reflectors. So we had to pair them per region, which allowed us to forego a full IBGP mesh. These route reflectors did their thing, and which is to say they hid routing information. This caused traffic flows which crossed regional boundaries to polarize onto single destination routers, causing them to become overloaded. We chased our tails a bit trying to balance things out with IGP metrics, but that didn't work. We then intended to deploy BGP add path to solve this issue, but after upgrading the code on all of our routers, we began rolling it out and quickly hit a couple of bad bugs. It was a very new feature. We then decided to take a much more pragmatic approach, and after validating that our routers had the resources to handle it, we simply deployed a full IBGP mesh. This immediately solved the polarization issue, and the lesson for us here was keep it simple until you can't. That being said, as our network continues to scale, we are working towards more of a regionalization model in our backbone routing policy, which should reduce the scope of some route types, which should help with things like that. Another load balancing issue we ran into regularly was under failure modes on the backbone. We grouped circuits with common paths and carriers into LACP aggregates, and these circuits would go down far more frequently than we would have liked, causing paths on our backbone to fail open. Even though we still had sufficient overall capacity, we would have to take manual corrective action to reduce replication traffic and possibly disable impaired aggregates. We see a simplified example of this here in the diagram. We have 600 gigs of demand from one facility to another. Suddenly, a failure on one of our northern transport paths reduces its capacity by 50%. And again, even though there's still sufficient overall capacity, we end up with the impaired path overloaded and discarding traffic. Finally, here we see the reduced demand to accommodate the failure, IP routing at its finest. We deployed MPLS with RSVP-TE to solve issues like this. Not only did it provide automatic rerouting of demand for failures like this, but it also provided much better overall utilization of available capacity on our backbone. We've come a long way on the backbone, made many improvements, including deploying MPLS with RSVP-TE, deploying QoS, moving from 10 to 100 gig waves, and improving the way in which we alert upon reduced capacity on the backbone. All these things have helped to lower our on-call page volume by over 60%. The final area of focus is data center. Our first data center deployments were fairly typical. They followed the traditional hierarchical model with collapsed core. We ran OSPF. Each cluster was a stub area with area 0 residing on the backbone. As we grew and built more clusters, we quickly decided to move to BGP in the data center network. We found BGP easier to support and troubleshoot. BGP has a mature multi-protocol functionality, which we leverage for IPv6. And it also provides a means of route classification and control of route propagation. This proved very useful as we moved to more cost-efficient hardware, and we iterated on our routing design. We ran into some limitations with our architecture pretty quickly. We started to run really hot on the cluster routers. Utilization would routinely exceed 50% of capacity. It was important to us that we be able to quickly drain a node in any tier of our network at any time, Even more importantly, we needed to be able to lose a node in any tier and not impact user traffic. Further, the cluster routers were fairly expensive, largely due to the ASICs that they utilized. These ASICs come at a premium due to things like route scale and deep buffers, neither of which we really needed in this particular aggregation tier. To solve these problems, we moved to a 4-post design, doubling the number of cluster routers. Not only did this solve the immediate capacity issue, but it also increased the usable capacity of each cluster router. Let's assume that 90% is the maximum safe utilization of a cluster router. This means that in a 2-post design, we can only safely run each node at 45%. In a 4-post design, we're able to run each node at almost 68% and easily lose or drain a node. At 45%, we can actually lose or drain 2 nodes at the same time. As we moved to the 4-post design, we also moved to more cost-efficient hardware, and this change in hardware allowed us to allowed us to more than double the usable safe capacity of a cluster while also reducing its cost by about 15%. This 15% does include the cost of additional optics required. In addition to the cluster routers running hot, the data center routers were also running extremely hot. Not only were they handling all of the internet traffic for a facility, they were also handling all of the traffic in and out of the clusters. This is a good time to mention that the data center routers are really expensive. They're great routers. I'd be willing to bet many of us in this room have relied upon them heavily, but they're expensive. They have custom ASICs, deep buffers, route scale to handle feeds from all of our peering routers, and they do RSVPTE really well. None of these things was needed for our local intercluster traffic. Taking a step back, we realized that the traffic hitting our data center routers fell into 3 categories. The first was north-south internet traffic, the second was interfacility traffic, and the third was local intercluster traffic. Further, each of these categories had a distinct set of requirements. We were really overloading the data center routers, the data center router platform, and it was really expensive. By providing unique paths for each type of traffic, we were able to optimize the associated hardware platform for cost and capacity. We started by deploying a new tier in our data center network to handle local intercluster traffic, which we called the cluster connector, or CC. We only needed a few protocols and IP routing from this platform, so it was cost efficient. We initially deployed this new tier behind the clusters in a facility, and this immediately provided some headroom on the data center routers. More importantly, the risk of intercluster traffic overrunning north-south client traffic was greatly reduced. We eventually moved this new CC tier up from behind the clusters to sit between the cluster routers and the data center routers. This provided many benefits, one of which was it allowed us to take advantage of the fact that the clusters would run much hotter when they were first built. More specifically, it allowed us to be flexible in how we utilize the capacity into a facility while minimizing the total number of required ports on the data center routers. The next step was interfacility traffic. We deployed another new tier, which we called the Data Center Connector, or DC. The requirements for this platform were slightly more demanding. Because it would use our backbone, it needed to support MPLS and RSVP. However, by separating the requirements for this type of traffic, we were able to qualify a platform at a fraction of the per port cost of the data center router. This further reduced the load on the data center routers and also allowed us to differentiate between interfacility and edge LSPs. And finally, the 3 groups of traffic were now on distinct paths and platforms, allowing us to scale them independently. Our data center network has come a long way. We continue to make improvements. We recently completed our IPv6 deployment, and our entire network is now, from the edge to the rack switches, dual stack with IPv6. We're very close to removing the hardware load balancers from our network. In fact, the last set of VIPs is scheduled to be moved later this week. We continue to iterate on driving down the cost of our hardware platforms, and we're currently working on the next generation of our architecture, which will include moving to 100 gig, an all eBGP design, and a scalable fabric topology. While our Great Base Jump migration is complete, we still maintain a strong partnership with AWS, and we're grateful to them for their commitment to their customers. At almost 700 petabytes, we continue towards our first exabyte of user data. It's worth mentioning again, our network is now dual stacked end-to-end with IPv6. Our desktop client now supports IPv6, and our traffic team is now currently working to make our front ends available natively via IPv6. Our performance optimization at the edge has improved the median upload and download speeds for our users, anywhere from 40% to 300%, depending on their location. We continue to build POPs and build out our edge, and we have, I think, at least 5 more scheduled this year. We also continue to iterate on hardware and software, working to further optimize the cost of our infrastructure. Thanks very much.
Wow. Thanks a bunch, Jason. That pretty much covers the whole thing from data center to aggregation to backbone to edge. There's got to be some questions here, so we'll send folks, if we can have folks coming around with the microphones. I think they're coming. Oh, there's one right here. Great.
Hi. Thanks for the talk. So I'm not sure if I missed this. So generally, can you describe how you map users from different areas of the world to different POPs you have? And also, second question is, since you have POPs, instead of besides the latency wins you have for the terminating the SL connection earlier, do you cache contents in the POPs? Thanks.
So I think the first question was how do we get customers directed to certain POPs, and that they're geolocated using a DNS service. And I think the second question was, do we do any caching? And the answer to that is no. So we just do we optimize on TCP and SSL, but we don't actually cache any user data. We do make use of some CDNs, but I think it's a very small amount for static content for things like web and stuff.
Hi, thanks for the talk. So doing BGP traffic engineering at scale is a complicated task. I tried it before, right? So there are a few tools available to open source. There are some vendor tooling. Could you share what's been used to provide kind of overall view? You're geographically dispersed. How do you automate provisioning, prepending? How do you tweak BGP metrics to provide proper load balancing?
If I understood the question correctly, yes, traffic engineering is fairly complicated. We are still working to improve a lot of our automation and our tooling. I think the best answer I have here is that we're currently working on iterative steps in configuration management. So we've got configuration generation covered. We've got push tools going, but we're still making strides in terms of more advanced forms of configuration management.
Hey, Jason. So
hey.
Two questions for you. One, what's your cluster size? Your 4-post CRs? And two, how are you handling geolocation for your user data or any data localization?
I'm not sure I can say how big our clusters are specifically, so I won't answer that question. And the second question was, how are we handling the geolocation for the customers? Customer data, yeah. So because we put such an emphasis on optimizing customers' connections to their data at the edge, where the data actually lives is less important. We are working we do have some plans to build out data centers potentially in other continents, but right now we're just sort of getting started in that vein.
Hi. So I have a question. First of all, I'm happy to hear that you think that peering is not only cost-effective, but also performance-effective. And I think some people in this room wouldn't agree with that, but I agree with you. And as you see, I'm wearing IPv6 T-shirt. So you did speak about IPv6. I noticed that you have IPv6 on the edge, but you didn't speak about the performance difference between IPv4 and IPv6. So even if the infrastructure is the same, even if you use the same internet exchanges, the performance varies between those two protocols. And the third question is, so that's on the external part, and what are the IPv6 plans on the internal part, on the data center side? Thanks.
So I don't think the first one was a question. I think it's awesome that you agree with me. The second one, difference in performance between IPv4 and IPv6. I've not shared that yet because we are not completely yet natively on IPv6 on the front ends, so I don't have a lot of data there. But I do expect there to be a performance gain going to IPv6, especially with mobile. Around IPv6 within the network, I think was your third question. We've sort of taken the approach that network first. So we're now dual stack completely end-to-end in the network, and our traffic team is now working on getting the front ends available via IPv6. There's going to be another step, which is probably a much longer tail on that one, and that's getting all of the hosts configured with IPv6 and then evaluating what services will actually live on IPv6. We're not at the scale where we're depleted on 1918 private IP space. So we don't have a strong motivation to go completely all only IPv6 on our internal network.
We had a question up here.
Hi, I have a question regarding the data center. So you said like you are, building or just deploying more data centers, right? So do you have a master data center, or how do you update, or how do you propagate the updates from one data center to the other to make sure there's least latency when the client is trying to get the data?
We do not have a master data center, no. Maybe a good way to answer this is when new customer data comes into the system, it's located in one data center, typically the data center that they're closest to, but that's not always the case. And then the data gets replicated to one other region at a minimum. So whichever one the data first lands in sort of guides which one it will be replicated to.
So the replication is real time or background, or will there be consensus, like differences, or?
It happens as soon as the data lands. I wouldn't say it's necessarily real time.
Okay.
It is fairly asynchronous in that regard, from the user's perspective, anyway.
Okay, so there can be, like if I'm viewing my data from one data center, and if I go to another location, there can be cases when I'm not going to get the updated.
No, you would always be directed to. So the application has awareness of that. So so it knows that where the original data is. So you'll be directed to that location until it's been replicated out.
Okay.
Does that answer your question?
Yeah, it does.
Okay.
Thank you.
Hey, so you said you're terminating the SSL to the POP. How are you securing data to AWS?
How are we securing data to AWS?
AWS, yeah.
So when we were pulling the data out of AWS, we were making calls to S3, so these were secured with SSL.
Any other questions? All right. Well, thanks so much, Jason. Thank you. Thank you.